Hi, my name is Kendra Johnson, and I'm a seismic hazard scientist at GEM. Today I'll be presenting on behalf of the GEM hazard team the PSHA model that we used throughout this project. So it wasn't an objective of this project to build a standalone PSHA model. So instead we used an existing model that covered a larger region. And we looked into this model and identified areas that we thought we could improve upon, specifically with the aims of this project in mind. So we introduced some changes to the seismic source characterization as well as the ground motion characterization. Throughout this presentation, I'll explain to you what these changes are, and I'll show you the impact that they have on the hazard results. So I'll very briefly describe the starting point, the model that we began with, and I refer you to the publications of Nath and Thing by Jam if you're interested in reading more. This is a model developed by researchers at the Indian Institute of Technology to cover Bangladesh, Bhutan, Nepal, and India. The seismic source characterization uses 3 seismic source models. All of them are based on distributed seismicity. So the first is an area source model, dividing the area into polygons, and then the same polygons are used in the other 2 source models, which use gridded seismicity with smoothed rates that depend on the past occurrences of earthquakes. These 2 different layers are calibrated with different ranges of magnitudes from the observations based on the minimum magnitude. The ground motion characterization uses a multi-model approach to capture the epistemic uncertainty in ground motions, and several of the adopted models are meant to be used specifically in this region in India. We've used this model since 2018 in GEM's Global Hazard Mosaic. So I'll just briefly introduce you to what that is, since I'll refer to it a few times throughout this presentation. GEM maintains a database of hazard models that are all developed in the same format, the OpenQuake Engine format. This is a map showing the different models and their domains that they cover. They're sometimes managed by the national agencies that oversee the area, or they're sometimes developed by more independent scientists, such as in the case of India. And we keep them together as a collection and use them for various activities at GEM, including to make the global seismic hazard map. So in the box here in red, this is the model that I'm describing now. The seismic source characterization used in this model is mostly based on PhD work done by Thing by Jam, and the main data used is an earthquake catalog also developed within this PhD, which includes instrumental records as well as historical ones dating back into AD 819. They also used focal mechanism data and published literature as well as paleoseismology. So the main construct of the seismic source characterization is that the Earth is divided into 4 layers based on depth. The first 25 kilometers and shallower, and then increasing in depth until reaching 300 kilometers. And each layer is divided into polygons, which are assigned a dominant focal mechanism as well as a Gutenberg-Richter magnitude frequency distribution, with Mmax defined according to any type of record of past seismicity. So this same characterization is used for the area source model as well as for the 2 smooth seismicity models. The ground motion characterization, again, uses the multi-model approach, and I won't go into detail on which models are included here because I'll describe this a lot in detail later, but I will mention that a few of the models that are included are models that are developed particularly for use in India. So when we started this project, the first task was to review the PSHA model and try to understand how well it would work with the applications in mind for this particular instance. So in this case, we were thinking not only of PSHA, but also of liquefaction and risk calculations. So in the seismic source characterization, we especially focused on the geometry of the ruptures that were generated by the models, since these ruptures are used specifically in later parts of the project and workflow. So we noted that several sources produce ruptures that are magnitudes greater than 9. And because distributed seismicity sources are used to model these, sometimes we found that the ruptures were not realistic and could potentially be causing problems in these various applications. So we reviewed the nodal plane orientations in the northeast part of this model as well, and tried to ensure that these were compatible with observations as well as the logic of the tectonics that are observed. So the first thing I'm pointing out here is the ruptures in pink. These are ruptures generated by sources that represent the main Himalayan thrust. The surface trace of this thrust is denoted in yellow, and you can see that to the east, some of the ruptures in pink are deviating from the strike of this structure, and they're actually crossing Bangladesh when, in fact, we would expect them to instead be to the north side of this yellow line. So we took a look at which sources were actually producing these ruptures, and we found that the ruptures that are magnitudes larger than 7.5 are produced predominantly by these two area sources, distributed seismicity sources in the center of the main Himalayan thrust. The ones that are shown in brown on the bottom image here. However, there are a number of different sources also modeling the smaller earthquakes on the main Himalayan thrust. So when we actually plotted the rates of the ruptures based on their hypocenters, the smooth seismicity models actually do place most of the rates along the fault where we would expect the surface of the fault to be. So what we propose is to move the largest ruptures onto a fault source rather than distributed seismicity, such that the ruptures are constrained to the fault source and therefore produce reasonable rupture geometries. So to do this, we turned back to the global hazard mosaic, and we looked at the adjacent model to India, which is the China model. They share a border at the main Himalayan thrust, and so the sources are covered in both models. So we turned to the China model to see if there was something there that we could use instead. So the China model uses a simple fault source constrained by slip rates to cover the main Himalayan thrust. So we took this fault source. It has a dip of 15 degrees to the northeast and it extends until 25 kilometers depth. We used this simple fault source from the China model to replace all of the ruptures with magnitudes larger than 7.5. And so for each of the source models in the logic tree, we actually used two different versions of this source, and we equally weighted them in the logic tree. We always used the same geometry, but we used two different sets of occurrence rates. The first one were those that were originally assigned in the China model, so this would be a tectonically constrained instance. And then in the second one, we used the rates that were assigned to other sources in the India model, and we simply moved them from the area sources onto the fault sources. We did a similar evaluation of the onshore extent of the Arakan Trench, which is covered by active shallow crustal sources that produce ruptures that bisect Bangladesh as well. So the instance is similar where the hypocenters are well represented. However, the ruptures are not confining to the logical structure that we see here. And so in this case, we turned again to another model adjacent to the India model. This one's covering Southeast Asia. And we moved the highest magnitudes onto a simple fault source, simply taking the geometry from the Southeast Asia model. We also found that some of the source zones in the northeast part of the model, quite close to Bangladesh, were producing ruptures that we thought had surprising focal mechanisms relative to their expected one. For example, we were seeing strike-slip earthquakes in the slab that were perpendicular to the trench axis. So in order to understand whether this was practical, we looked to some recent literature, including a focal mechanism compilation by Fadil et al. And I won't go into great detail on all of the elements here. So I refer you to the paper, both the one for the PSHA model, as well as the recent focal mechanism compilation for those who are interested in knowing more. But I'll just summarize a few main points. The first thing is that the authors of the PSHA model noted that actually there's intraslab sources extend from 25 to 70 kilometers, and they do this even though they know that it may include crustal earthquakes, because it's consistent with the way that the intraslab GMPEs that they used in this region were defined. So some earthquakes as shallow as 25 kilometers were included in those data sets. We also looked at the focal mechanism orientation seen in the model as well as in the new compilation, and we found that there are tectonic explanations that can account for these. However, in some cases, we thought it was appropriate to add an additional focal mechanism. So, for example, a north-south oriented thrust mechanism that's along the IMB range front in some of the largest intraslab sources that occur in the model. The final change we made to the seismic source characterization is in regards to the tectonic region type. So we decided to move all of the sources that are pertinent to the main Himalayan thrust onto an independent tectonic region type. So some had formerly been assigned interface and some had formerly been assigned active shallow crust, and we decided to merge this into a single independent tectonic region type. We also reassigned one of the larger area sources in the eastern part of the model that was labeled as subduction because it predominantly included thrust faults. However, we changed this to an active shallow crustal domain since it doesn't actually occupy a contact between two plates. And finally, we merged the active shallow crust normal and reverse strike slip tectonic region types into a single one because we thought this was more appropriate in terms of correlating the epistemic uncertainties in terms of tectonic region type. Okay, moving to the ground motion characterization, we reviewed the GMPEs that were used in this model, in part because a lot of new models have been developed since the model was first developed, and also because we are now using the model for more applications than may have been initially envisioned. For example, the risk and liquefaction applications. So to do this, we used criteria from Stewart et al., who suggested GMPEs for use in global seismic hazard maps and applications. And we evaluated the GMPEs on a per tectonic region type basis. We looked at their spectral shapes, we looked at how they handled magnitude and attenuation terms, and we looked at the types of data that were used to constrain the models relative to what's included in the seismic source characterization that they're being applied to. So starting with the active shallow crust, the GMPs listed here are the ones that were included in the original model. So the first thing that we noticed is that the Cano GMPE that's used widely in this area lacks a magnitude saturation term, and that can cause unreasonable estimates for the largest earthquakes included. So we removed this GMPE. We also removed the Sharma GMPE because the linear scaling of magnitude made for unrealistic ground motions in spectral shapes for the largest magnitudes, which are quite important to the hazard calculations done here. The data for this GMPE only extended up to magnitude 6.8, so we thought this was an appropriate decision. Without this, we were able to combine the two tectonic region types into a single one for active shallow crust. We still didn't have enough strong motion data to select the GMPEs, so we chose to attempt to move toward consistency with other GEM regions, and so we looked to the China model, which proposes a 3 GMPE logic tree. However, we decided to eliminate the one by Kautzi, which doesn't cover magnitudes larger than 7.9. Then we decided that in order to best cover the epistemic uncertainties, we would produce a logic tree that included scaling factors applied to the median of the other two GMPEs. In the case of the intraplate margin, we found that there were GMPEs not including a site term, namely the Toro GMPE, and so we replaced this with one for Yenyer and Atkinson. We also removed Sharma for the same reason as above, and we've also removed the Neth et al. GMPE since it misses the main periods used for risk, and also had some concerns with the PGV estimates that were coming from this GMPE. So we replaced these logic trees with a 2 GMPE logic tree that was used for both the upper and lower margin. For the stable shallow crust, which covers the majority of India itself, we used evidence directly from the Stewart report to remove the GMP by Raghukant and Iyengar, which showed that there were nonlinear effects that were super strong, and the amplifications had significant variations among the periods. They also noted that the standard deviation was a lot lower than for other models, and so for event-based calculations, this might not be appropriate. We also replaced Toro according to the same reasons as before, and so in the end, we have the same logic tree for the same stable shallow crust as for the interplate margins. In the case of the subduction intraslab sources, the original model defined 2 different regions, one for the Himalayas and one for the subduction zone to the southeast. These different regions were applying some different region-specific terms that we couldn't find a tectonic explanation for, and so instead we replaced these with recent global models. We also eliminated an India-specific GMPE because it was constrained by very few earthquakes at large distances between the rupture and the sensor, which didn't cover the site to source distances that we're seeing in the model itself. And finally, for the subduction interface, we have 2 things to consider in this instance. The first is the main Himalayan thrust had some sources in the original model, some portions that were originally classified as subduction interface. However, we don't consider this structure to be a true interface nor a true active shallow crust. However, we don't like to mix GMPEs from different TRTs in studies like this one because while this might lead to an improved mean hazard calculation, no single realization is realistic, and this is especially problematic when we're using individual ruptures in event-based analyses. So instead, we again aimed for consistency, and for the main Himalayan thrust, we used the GMPEs as in the active shallow crust. This is the same approach that's used in China. The main Himalayan thrust is considered an active shallow crustal domain. And finally, for the subduction zone to the southeast, we used the interface versions of the GMPs selected for the intraslab. Putting this all together, here we see 2 hazard maps that compare the original hazard PGA on rock with 2% probability of exceedance in 50 years to the final result for the tailored model. That one's shown on the right. So the main 2 outcomes here are that the hazard decreases relative to the original model, and the impact of the relative tectonic structures is still evident in the hazard pattern, especially in the southeast portion of the model. So to conclude, I'll just summarize the main advantages of the new model. The tailored model is including rupture geometries that we believe better represent the types of earthquakes and their geometries that we expect to see in this area. We also are using GMPEs that we believe are better constrained and that are sufficiently flexible to be used throughout all the objectives in this project. And finally, the hazard in the tailored model that we presented today is lower than in the original one. So thank you very much for your attention, and I will take any questions.